Okay guys, so today we're going to look at a new kind of sequence, and these are going to be geometric sequences. So if you look at these first two examples, these are both examples of geometric sequences. So you can try and look and see what's common here. Okay, in that first sequence, to get from term to term, I have to multiply by 2. And if I look at the second one, I have to divide by 3. So if you look, I'm multiplying or dividing by a constant number. So that's what makes a geometric sequence different than those arithmetic sequences we learned about. Okay, so we also, because these are common, we have a formula we can use to help us identify these sequences. So what I have, a sub n, which again still stands for my nth term, a is still going to be my first term, just like it was in the previous formula. N is still the number of terms, the term number. And the only one that's new here is r. So on this formula, R stands for the common ratio. So just like the common difference, except instead of what I'm adding each time, this is what I'm multiplying by. Now this number can be a whole number or it can be a fraction. So if that number is less than 1, that's when I'm actually decreasing. Okay, so we can look at this to help us on that first example. So that first example, if I want to figure that out, I want to find my nth term. So the nth term on that next example would be a sub n equals my first term, which is 2, times my common ratio, which is 2 to the n minus 1. And that's how I'd write my nth term. Now, what I'm going to be careful not to do here is I'm not going to write this as 4 to the n minus 1, because that's not the same thing, because that n minus 1 is not on both of those terms, so I cannot combine those together like that. It wouldn't work out the same way. And you can tell, for example, if I used 4 to the n minus 1, if I plugged in 1 for my first term, I would get 4 to the 0, which is not the same thing. So just be careful. Leave them written as multiply. Don't actually multiply them together. We don't want to do that. Alright, so if I look at my second example, I would take my first term, and then to find the common ratio, remember, it's what I'm multiplying by. So dividing by 3 really means I'm multiplying by 1/3. And that's how I would write it. Okay, now, so to find the nth term of this example down here, this one's a little bit different. So if you look, my first term is -3. So I have -3 times whatever my common ratio is. But if you look, this one's a little different because to get from -3 to 1, I had to multiply by a -1/3. Same thing for every term that follows. So I actually have to multiply by a -1/3 to the n minus 1. Okay, so again, just like there was for the other sequences, I still have a partial sum formula that I can use. And again, it uses the same letters here, where a is my first term, r is my common ratio, and n is the number of terms I'm adding. So if you look at this example down here, I'm going to find the sum of that series. So if you look, I have a, which is my first term, and I can determine my common ratio. Every time here, I'm multiplying by 2 to get to each next step. So I have my r as well. So I have my a, and I have my r. What I'm missing, though, is my n. Well, I know that the last number is 768. I don't actually know which number of my sequence 768 is, so I have to solve for that first. So in order to solve for n, I'm going to use the sequence formula that we just learned. So what I'm going to do is I have 768. I know that's going to be equal to a times r to the n minus 1. And I just need to solve that equation for n. So in order to do this, we're just solving an exponential equation. So the first thing I would do is I would take 768 and divide it by 3. And then the easiest way to solve this one is just to rewrite 256 with the same base. So 256, that's going to be the same thing as 2 to the 8th power. And the only way for 2 to the 8th power to be the same thing as 2 to the n minus 1 is if 8 is equal to n minus 1, which means that n has to be 9. So once I know what n is, I can actually use my partial sum formula to solve this equation. So what I would do here is I would take my partial sum formula. Now I know I'm finding the sum of 9 numbers. My first term is 3, and I have 1 minus my common ratio to the 9th power, divided by 1 minus my common ratio. And then I can just do that math to get my answer. So I'm going to end up with 3 times negative 511 over negative 1, which gives me a final answer of 1,533. Okay, now there is one kind of special sequence that we need to look at, and these are what we call infinite series. Okay, so these are series where the one we just did, it was finite. It had an end. We knew the last term I was adding. But sometimes we're going to need to try to find the sum of a series that just keeps on going. Okay, so in some cases we can do this. In some cases, though, we can't. So if you look at this first example here, 1 plus 2 plus 4 plus 8 plus 16. If I were to keep adding all those terms, it would keep on going to infinity. There's no way I could ever find the answer for that. But then if you look at this second example, this one actually does have a possible number that it's going to go towards. So if you think about this, what I have here is I'm going to take a half. And to that half, I'm going to add a fourth. To that fourth, I'm going to add 1/8. To that, I'm going to add 1/16, 1/32, 1 over 64, and it's going to keep on getting half and half and half and half until I get closer and closer and closer to 1. So some of these series, even though they do keep on going with a common ratio, they actually do have a sum that we can find. But the only way they're going to be able to is if it's a specific kind of ratio. So if you look, the ratio of that second equation was 1/2, but the ratio of the first equation was 2. So the way we can tell is if that ratio is less than 1. Okay, so that common ratio cannot be greater than 1, or else it's never going to have an end to it. And if that is the case, if that ratio is something like 1/2 or 1/3 or 3/4, then I can use this equation to help us find my sum, where a is still my first term, and r is my common ratio. Alright, so if you look at this first example, this is an infinite series. It keeps on going, there is no end. So in order to find out if there is a sum, okay, I need to find out, first of all, what is my common ratio? So if you look at this question, my common ratio here, when I'm multiplying by each time, is a -3. And one thing, actually, something really important I forgot to add, that common ratio, the absolute value of that common ratio needs to be less than 1. So it's okay if it's negative, but the absolute value of that ratio needs to be less than 1. So the absolute value of my ratio here, which is 3, is not less than 1. So this equation, there's no sum there. There's no way we could find it. So we're going to say that that diverges. But if you look at this second example over here, every time I'm multiplying by 1/3. And since the absolute value of 1/3 is less than 1, I can find the sum of the series. So I'm going to use that last formula, where s equals my first term divided by 1 minus my ratio. So that means I'm going to do 27 divided by 2/3. Sorry guys, wrong button. So that's going to give me 81 over 2, or 40.5, which is about the same thing. And that's how we can find the sum of an infinite series.